In Robotics 1, we learned about the difference between open loop and feedback control. We learned that one widely used and widely useful type of feedback control is a type of linear control called PID. Here, P stands for proportional, I stands for integral, and D stands for derivative. Back in Robotics 1, we only got through the proportional part of this control. Here, we'll review what we learned about proportional control, and we'll move on to the integral and derivative parts. This is an appropriate time to be learning about this because in the last class we learned about stepper motors, which are a type of motor that can do position control without using feedback from a sensor. However, in robotics, there are certain situations where it would be useful to add some kind of a sensor to our stepper motor in order to allow it to do different kinds of operations. And in this lab, we're going to start learning about one of those applications, which is tracking a moving object. Now, when we are using feedback control, that means that we are getting our robot joint to go to a position by changing the speed of the motor based upon the difference between the position of the motor and the position that we would like the motor to be in. And since the position of the motor is changing all the time, we would have to do this operation inside a loop, where we continually read the joint position and maybe the position that we want to be at, and then change the velocity accordingly. This is an effective way to control the joint's position because it means that we can make the motor stop, that is, set the velocity to 0, when the motor is exactly at the position we want it to be in. We're going to start where we left off in Robotics 1 with our proportional control, but we're going to apply it to a different situation. In Robotics 1, we used proportional control to set the position of a rack and pinion that we used for a prismatic joint. We used an encoder attached to the shaft of a DC motor to provide the feedback. Today, we're going to use a camera to provide feedback to our stepper motor to do a tracking application. So you should already have your stepper motor hooked up from the last lab. Now, find the camera to stepper bracket in your kit. It looks like this. The two holes in this barrel look like they're the same size at first glance. If you have the wrong bracket, it will have the two holes different sizes. This other bracket is for attaching the camera to the DC motor. We want to find this bracket with the two holes that look like they're the same size. This is the bracket for attaching the camera to the stepper motor. Now, although these two holes look like they're the same, they're actually different. One end matches up with the camera shaft, and the other end matches up with the stepper motor shaft. So first, try to press one end of this bracket onto the camera like this, and try to press the other end onto the stepper motor shaft like this. And if it seems to be not able to press on, or if it seems too loose, you might have it upside down and try flipping it over and try it again. Then use two standoffs to attach the stepper to the board like this. The holes that we want to use are marked on the board. If they aren't drilled out for you, use a 3mm drill bit to drill the holes here. Then attach the motor like this. This will give you more stability while we do this tracking operation. Next, we'll write some code in PSoC to set the velocity of the stepper motor. Here's what we want our PSoC code to do. Wait until it receives a value over UART to indicate the motor speed. Then get another value to indicate the desired direction. Then use those values to set the motor speed, and then loop around and wait for a value over UART again. We're going to do our actual control code, the PID, in Python, which we'll be using to read the camera image. Now, in order to make this work, we need to be a little bit more efficient with how we set the stepper motor speed. In the last lab, we set the motor speed by calculating the length of a delay between steps, and then using CY delay to wait that amount of time between each motor step. That was an easier to understand way to do speed control, but now we don't want to do that because our code won't be able to do anything else while it is pausing between the steps. We would like the code to be able to check for a new UART value while it is pausing between the steps. In order to accomplish that, we're going to use PWM to make the stepper motor turn at a desired speed. This method is a little harder to understand than the first way we did it, but it's more efficient to run. So follow along and build your code as I do to set this up, and I'll try to explain what we're doing as we go. I'm going to draw here a time plot to illustrate what we want to be happening with our PWM signal in order to control the stepper speed. So this is time, and then this vertical line that I dashed here is the 0 ticks time. And then over here we have period number of ticks. Remember that a PWM signal repeats every period number of ticks of the clock. Now, in order to make the stepper motor run, I need to have 4 different signals. The first one, which I'll draw in red, I'll call this signal A. This is the signal that makes the first step happen. It energizes the first pole of the stepper motor. That signal should go on at 0 ticks, and it should go off at period over 4 ticks. Then I have to have another different signal that's off while A is on, and then it goes on immediately after A, and it should go off at period over 2 ticks. Then I need to turn on the third pole, so I have a third signal here that goes on at the time that B goes off, and C goes off at 3/4 of the period. And finally, I have to have a fourth signal that's off while A, B, and C are on, and then it goes on for the last 1/4 of the period. If I can create a signal like this will drive my stepper motor. So I just have to figure out how to make a PWM signal do this. Here's one way that we could do that. I'm going to draw a new plot here, but it also is a time plot. And this is 0 ticks. And over here is period number of ticks. Now, suppose that I have just 2 PWM signals. One of them looks like this. It's on for the first half, and it's off for the second half of the period. Then, suppose I have a second PWM like this. It's also on for half the time, but it has a phase delay of 1/4 period number of ticks. If I had these 2 signals, I could make 4 other signals out of this. I'm going to call the red signal alpha and the blue signal beta. If I could look at just the time when A is on and B is off and call that signal A, that signal would look like this. It would be on for the first 1/4 of the time and off all the other time, because the first quarter is the only time when A and not B is true. Then I could have a second signal that is alpha and beta. So this signal is only on when alpha and beta are both on. I'll call that signal B. and it will make a signal like this. It's on for only the second 25% of the time. Then I could have a third signal that is on when B is on but A is off. B and beta and not alpha. I'll call that one C. That one looks like this. And then lastly, I'll have a signal that is not beta and not alpha. And I'll call that one D. Like that. Now we're going to do this in PSoC. Create a new project and let's go get some PWMs. Over in the Digital Functions menu, drag 2 PWMs to the window. Then let's set up our inputs. Under System, go get a clock. And here we actually want to use the same clock for both of the PWMs. So just place one clock connected to the first PWM and then use this little connection wiring tool to connect that same clock to the other clock input. We're using the same clock because we want these two PWMs to be totally synchronized with each other. Now, under Digital Logic, go get a couple of logic lows and wire them to the reset. Now, let's take a look at these settings here. Make this a 16-bit, and we only want one output. I'll set the period to 100 for now, just so that we can see what's happening. We'll change this period later. Now, when I set the period to 100 and the compare value to 50, the signal is on for half the time and off for half the time, which is what we want for one of these two signals. Now, in the second PWM, I'll also make it 16-bit, one output, but select Center Align. And then for now, we'll set the period to something. I guess I'll do 10,000 here. 5,000. We just want the compare value to be half the period. We're going to go back and change these things later. So if I do this, Center Align, I now have the two signals that I want. One signal that's on for the first or second half, and another signal that is on for the last and first quarter of the period. Now we need to change our clock speed because our clock speed will determine the motor speeds that we can achieve. Set your clock speed to 10 kilohertz. Now take a look at this. If I switch this compare type 1 between greater and less, I will swap which half of the period is high and which half is low. This is also true of my second one. If I switch between greater and less, the signal swaps. This is how we're going to manage to reverse the direction of the motor. So you have to actually select firmware control here for the compare type. Firmware control means that we're going to be able to change this in our code, and that's what we need to be able to do in order to reverse the motor. Now, here's where we need to set up all of this and logic that gets the right signal to the right pin. Go get 4 pins and place them in the window. These 4 pins will be for the 4 poles of our stepper motor. And your clock here should actually be 10 kilohertz. Make sure your clock is 10 kilohertz. I made that mistake here before. And then the period should be 1 second. We want this because if the period is 1 second, we have the ability to get pretty much the correct range of speeds of the stepper motor that we want for our tracking operation. Now, in the menu on the right, scroll up to find the digital logic and find the AND junction. We'll connect the output of the AND to pin 1. So we'll do, for one of the two inputs to the AND, we'll do the first PWM, that is alpha, and then the second PWM represents our beta. So this will turn on pin 1 only when alpha, the first PWM, and beta, the second PWM, are both on. Now, one other signal that we want goes on when both alpha and beta are off. So I'll get a NOR junction. A NOR junction goes on only when both of the inputs are off. So I'll wire alpha and beta to the inputs of the NOR, and I'll call that pin 2. Now, another one of the signals that we want goes on when alpha is not on and when beta is on. Let's see if we can do that. So I put an and wire it to pin 3. Then I'll take a not junction here. So I'll do not alpha, and then I'll wire beta to the other side. So pin 3 is going to go on when alpha is not on and beta is on. So I have one more combination here. This one will go on when alpha is on and beta is not on. So I'll find alpha. Here's a wire that connects to alpha for the top. And then I need not beta. Alpha and not beta. So I have the 4 correct signals, but I probably don't have them in the right order here. We'll figure that out in a moment. Go to the pins. You can select whatever pins you want here. These just have to be the 4 pins that you've connected to In1, In2, In3, and In4 on your stepper motor. I connected mine to 01, 02, 03, and 04, but you can have these be any pins that you actually connected to your stepper motor. Okay, go ahead and program the PSoC. We've placed a bunch of things on the top design, so we want to check and make sure that this program goes through and correct any errors we have right now. Then go to your C code and clean it up a little bit. And all we're going to do here is turn on PWM1 and PWM2. Here, I'm going to make sure that the period and compare values are set the way we want them. I'll write 10,000 to the period and 5,000 to the compare value for both PWM1 and PWM2. Then program the PSoC, and here what you want to do after you've programmed the PSoC with just this simple code, watch what your stepper motor does. Your stepper motor should turn on A, then B, then C, then D, and then it should repeat. Or it should go D, C, B, A. Either one of those is fine, but it should go in either A, B, C, D order or D, C, B, A order. If it doesn't, swap around either the pins in your PSoC code or the physical wires that you have connected up until you get it to go in the A, B, C, D or D, C, B, A order. Once you have that figured out, come back here to the video and we're going to set the motor speed. So we'll create a new variable up at the top, float motor speed. And for now, we'll use units of steps per second for the motor speed. I'll set it to 10. Then I'll create an integer for the period. The way we're going to change the motor speed is by changing the period of the PWM. So we need to calculate the period based on the motor speed. If we take 4 times the clock speed, that is ticks per second, and we divide that by the motor speed, which is in steps per second, and we know that there are 4 steps in every period number of ticks, this will allow us to calculate the period, the number of ticks per 4 steps. So instead of writing a constant 10,000 to each of these 2 periods, we're going to write the period that we just calculated. Then, instead of writing a constant 5,000, we have to write to the compare value half the period. All right, program the PSoC, and your stepper motor should turn at about 10 steps per second. Watch what the motor does and make sure that it actually turns at about 10 steps per second. If this is working and your motor really is turning at about 10 steps per second, let's go and make the motor able to turn in both the forwards and the reverse direction. To help you understand how we're going to do this, let's look back at our top design. When I double click on the PWM block and I click on this drop down here, we have a number of options. The first option is equal, the second option is less, the third option is less or equal, and so on. I can set which of these things I want to be here in my code, and the way I do that is by numbering each of these options. So equal is going to be the number 0, less will be the number 1, less or equal will be the number 2, and greater will be the number 3. So the way to reverse the direction is to swap whether this thing is less or greater in the code. I'll show you how to do that. Down here, I'll do PWM1, set compare mode, and I'll put 1 there so that it is less. And then PWM2, set compare mode, and I'll put 3 here so that PWM2 is set as greater. Now, program the PSoC and watch the motor. It should move in one of the 2 directions, either forwards or backwards. Then swap these around, put 3 for the first compare mode and 1 for the second compare mode, and run the code. Your motor should turn at the same speed, but in the other direction. Make sure that this is working consistently for you, and then come back to the video and we'll move on again. Now let's create a variable to indicate the direction. let's make 1 mean one of the two directions, we'll just call it forwards, and 2 means the other direction, which I'll refer to as backwards. Now, if direction equals 1, we will take the speed settings out because the speed is the same regardless of the direction. But we set the direction by setting these compare modes. So if the direction is 1, we'll do compare mode 3 for the first PWM and 1 for the second PWM. If the direction is 2, we'll do this in reverse. So I'm going to copy these 2 lines of code here. I'll highlight them and then Control C to copy and then paste them. And we'll swap the numbers, 1 for the first PWM and 3 for the other PWM. Now before we move on, we want to test this. So program the PSoC with direction equal to 1 at the top and watch what your stepper motor does. It should turn smoothly in one of the 2 directions. If it is turning smoothly in one of the 2 directions, go up to the top of the code and change direction to 2. And then test it again. Your motor should turn smoothly in the other direction. If that's working, we're now going to go set up our communication. Go to your top design, expand the communications window, and get a UART. Place the UART on the screen, and then go down to logic, get a logic low, wire it to reset, and then double click on the UART and set the bits per second to 9600. Back in main.c, we will start the UART 1 and we'll create an unsigned 8-bit integer called receive1. Remember that we're going to receive 2 things, one thing for speed and one thing for direction. So I'll have receive 1 and receive 2. Now we want to do all of this inside of the for loop because we need a loop for our control. So the first thing we'll do in the for loop is receive 1 is UART1 get char. Then we want to keep checking as long as we haven't gotten a value. And whenever we haven't gotten a value, we think that we've gotten the value 0. So while receive 1 is 0, we will continue receiving a value. Then I'll copy these 3 lines and do it again to get receive 2. One of these 2 numbers is going to be a speed number, and the other number will be a direction number. Now, it's possible that these 2 numbers could get out of sync, so I don't necessarily know which of these 2 numbers is direction and which is speed. So I'll say if the receive value is either 1 or 2, that's what these 2 vertical lines mean, then the direction will be receive 1 and the speed will be receive 2. I'm going to assume that we won't ever be trying to move 1 step per second or 2 steps per second. But even if we are, this will end up working correctly anyways. So else, if receive 1 is not 1 or 2, then we know that receive 1 is actually the motor speed. So we'll do direction is receive 2 and motor speed is receive 1. So now that we have direction and speed from the UART, all of this stuff for setting the speed of the stepper, we want to do it inside of our loop. So I highlight all this and cut it. And then I scroll down here and I paste it after the else. And I'll try to line things up correctly so that we keep everything nicely organized and understandable here. Now, there's one more thing you need to do here. After we set the direction of these two PWMs, we also have to make sure that the clock is synchronized between the two PWMs. The way we do that is by writing the counter value to 0. This is like resetting the stopwatch. If we always reset the stopwatch when we change directions, that will keep our 4 steps in sync with each other. Otherwise, they can get out of order. So I'll always write the counter value to 0 in this if. Now, before we actually test this, there's one more thing that you have to do. Go to your pins window and make sure that the RX is set to 12.6 and the TX pin is set to 12.7. In PSoC 5, it really matters which pin you select is the RX and the TX. So go set your pins and then program the PSoC and make sure that it goes through. If your compile and program is successful, the PSoC isn't going to do anything interesting yet. We have to send it some values. So go ahead and open up a new file in Python and we'll write some test code to be able to set the direction and speed of the stepper motor from Python. In your code, we'll start by importing some things. We'll import serial and we'll import numpy as NP. We'll import time and we'll also import CV2 because later on in a moment we're going to use the camera. So we'll create a serial object, set the baud rate of the serial object at 9600, and then we'll set the port. Remember that this is a COM port and we need to know which COM port is your PSoC, and you do this from Device Manager. Open up your Device Manager, go to COM ports, and my COM port is COM24. Your COM port will almost certainly be different than this. So I'll put in COM24 for myself, but your number here is different. You have to find it from your Device Manager. Then we do sir.open. Then I have to create a byte array that we're going to send. And this byte array will actually only have 1 byte in it at a time. This first number that I've put here is the motor speed in steps per second. So then we'll do sir.write, and I want to write I. Then I want to do a little sleep because I want to make sure that the PSoC is ready to receive my value before I send it. So I'll just sleep a little while. Then I create another byte array. This one is the direction. So here you want the number to be either 1 or 2. It means either go forwards or go backwards. That's the direction. And then we write that value. Now run the code and your stepper motor should start turning in the direction you've indicated and the speed that you've indicated. Try this a couple of different times, putting in different speeds and directions. If this is working, try to figure out what's the fastest speed that your motor can reliably do. Increase the speed until the motor doesn't respond correctly anymore, and take note of that. We'll use that maximum speed as a limitation in our control code. So for me, 80 still works fine and 120 still works fine. Just test some speeds and see what's the fastest you can go. Now you might notice that when you reset your PSoC so that it restarts its code, it starts turning right away by default. I would prefer if the motor doesn't turn at all by default. Go back into your PSoC code and double click on the PWM block and set the compare value to 0 for both of the PWMs. This sets their default values so that when you run the code initially, it won't go anywhere. Program the PSoC and test this to make sure that this worked and your stepper motor doesn't go anywhere. Okay, now it's time to go and set up our actual control code. The sensor feedback we're going to use is the location of an object in view of the camera. We already have lots of code for finding the location of objects, and for now we're going to do a simple object location algorithm. If you do this final challenge, you will learn how to track different kinds of objects using different methods. For now, we're just going to track the location of a red object. We already have this code, so I'm not going to develop it for you now. You probably already have it. Here's what you should have. You should have a while one loop that comes after a video capture line. So a video capture line and then a while one loop. We take an image from the camera, separate it out into red, green, blue, find the red only image, then we limit the image to be between 0 and 255. We threshold the image to make it black and white. Then we change it to a UART 8, and then we show the two images. I'm going to change the name here to red only. Then we limit the value so that anything greater than 0 is 1. And then we do this thing for finding the column location of the object. That's all we need here because the column location of the object is what we're going to use to do our control. So take all of this stuff for writing the speed and direction and copy it and then comment it out up here. Then after we have the column location, paste it down here. And you'll have to take out this sir.close line. I won't notice that until later. Now, to do our control, the first thing we need to do is calculate the error in the location. We want the red object to be in the center of the frame. So since the frame is 640 pixels wide, I can calculate the error by doing the column location minus 320. Now I need a KP value for my proportional control, and then I set the speed as KP times the error. This is proportional control, just like we did in the first semester. Now, if the speed is greater than the maximum speed that you can do, which I'm going to use 120 here, you can use whatever you found as your motor's maximum speed. If I calculate the speed to be greater than 120, I'll set the speed to 120. And if I calculate the speed to be less than negative 120, I'll set it to negative 120 so that we're never trying to go faster than the motor can actually do. Now I'll set the direction to 1 by default. But if the speed is less than 0, then I want to switch to the other direction. So I'll make the speed equal to negative speed so it becomes positive. And then I'll set the direction to 2. I don't yet know if 1 and 2 are correct. We'll find out by testing. We might need to swap around 1 and 2 here. Now instead of sending the number 120, we want to send the number speed, and instead of sending a constant 1 or 2, we want to send direction. And then delete this sir.close because we don't want to close the serial port every time through the loop. And I'm also going to make this sleep a little bit less so that we have less of a delay here because I need a delay after the second write also. So together we'll have a 0.1 delay every time through the loop. All right, now reset your PSoC and then run this module. And hold a red object in the view of the camera. If the motor turns to avoid the red object, then that means that the direction that we've set up is the wrong direction. In my screen here, my camera is always turning away from the red object. So the way I'm going to fix that is change direction to 1 or 2 here and then 1 over here. And then I'm going to test it again. I reset my PSoC so that it's waiting for values. And then I run this code. I hold the red object and my stepper should turn to center the red content in view. When you move the red object, as long as it moves still in view of the camera should turn to center the object. Now, my camera right now is unstable. It's oscillating so that the red object moves back and forth continually in the window. That indicates that my KP value is too high. I'm going to go back up here to where KP is equal to 1, and I will reduce it. And I'll test again. I'll move the red object, and the camera should turn to keep the red object in the view. As long as you have a stable system here so that the motor and camera isn't oscillating continually as you move the red object around, then we're good to go, and we're going to move on to the next step. Now, this line in the code right here changes the speed based on the positioning error, how far away the motor is from the position that we want it to be at. Now, when the error is 0, the motor is in exactly the right position, the speed will be 0, the motor will be stopped. When the error is positive, the motor hasn't moved far enough, the speed will be positive so that the motor will move forwards towards the target position. And when the error is negative, the motor has moved too far, the speed will be negative so that the motor will move back towards the target position. Now, sometimes proportional control will be perfectly acceptable for your robot motion, but other times you will need to achieve motion that is better in some way, smoother, faster, more accurate. In these cases, we have the option to add some features onto our proportional control equation. One feature we can add is derivative control. Here's how derivative control works. Derivative control helps to achieve smoother motion, that is, less overshoot, by adjusting the speed of the motor based upon how fast the positioning error is changing. To implement it, we change our speed equation like this. I'll add on KD times the derivative of the error, which I'll call d error. Now, of course, I have to set KD here. For now, I'm just going to set it equal to 1, but just like for KP, we have to tune the value of KD. Then we have to calculate the value of d error. Now, the first time through the loop, I just need to give it some kind of a value. So before this loop even starts, I'll do d error is equal to 0 so that it has some kind of value. And then down at the bottom of this loop here, we do d error is equal to error minus last error divided by the amount of time it takes to go through this loop. I'm going to estimate the amount of time it takes to go through this loop as 0.1. And the reason why I'm estimating that is because I have a sleep of 0.5 here and a sleep of 0.5 here. Of course, all the rest of the stuff in this loop doesn't take 0 time, so my estimate of 0.1 isn't going to be correct. But because I get to pick the value of KD, getting exactly the right value here isn't that important. So one more thing I have to do is take care of this last error. Every time through the loop here, let me go back up to where we're calculating error. right before we calculate a new error value, I'm going to do last error equals error, so that when we change the value of error here, last error is already saved as what error was before. And I actually put this in the wrong location. Take this last error equals error out, and we want to do that right here after we calculate the derivative of the error. Then up here where we set D error to some initial value, we have to do the same thing for last error. Now let's try it. Now, whenever we're adding some new control feature, we always want to start off by adding in that new control value only a tiny bit. And we also want to compare it to how it is without that feature. So let's set KP equal to something that gives us overshoot. I'm going to use 0.8. And I'm going to set KD equal to 0. And I want to watch the response with just this value of KP first. I'll run the module, get it so that the red object is being centered, here's a centered red object. Let me turn it so that there isn't other red stuff in the view. And then I'm going to do a step test. So I'm going to slide the red object to the side of the screen and watch how the response is. It overshoots and then it comes back. And then it overshoots a little bit more. It overshoots and then it comes back and overshoots a little bit more. Okay, now when I want to stop this and I don't want my motor to just turn all over the place, what I do is I hit escape to stop the Python code, and then I hit reset on my PSoC, and that makes my motor stop. Now I want to add in just a little bit of KD. Let's try 0.01 and see what happens. I'll run this module. Let it get the red object in view, and then I'll slide it over to the right. It still overshoots, but I think it overshoots less. It's a little bit hard to tell. You want to try it a number of times and see what you observe. There should be less overshoot. You should be able to find a KD value which gives you much smoother motion. Let's try using a little bit more KD. So I hit escape to stop my Python code, and then I hit the reset button on the PSoC. What if I do KD is equal to 0.1? Let's try that. I wait until the red object is centered, and then I slide it to the side of the screen. This behavior is worse. I have way too much derivative control here. Let's try 0.02. Try some different values of KD and make observations about the behavior of your controller. Then we're going to go on and add integral control. Integral control changes the speed of the motor based upon how the error adds up over time. The longer error is present, the greater the speed becomes. This is most useful when you have a situation where you just can't get rid of your steady state error. Integral control will also make the motor get to its target position faster. That is, the rise time will decrease. Unfortunately, integral control also makes the overshoot worse. That's one of the reasons why proportional, integral, and derivative control is often used together. Adding the integral control will make the positioning faster and more accurate, but will make the stability worse. In fact, here's a table that I have that summarizes the effect of increasing the gains of derivative, integral, and proportional control. So oftentimes, derivative control is added to improve the stability, decrease the overshoot, while integral control is added to improve the accuracy. So here's how we add integral control to our code. I'm going to put the integral control in before the derivative control so that we can take it out if we want. I'm going to do ki times the sum of the error. And then I'll do plus kd times d error, but for now I'm going to comment out the derivative. Here I need to add ki is equal to 0.01 or something like that. You always want to add in just a very small amount of integral control, because if you have too much, your system will go unstable. Now I need to keep track of the sum of the error. Just like we did with the other things, I'll initialize sum error to 0. And then down at the end of this loop, I'll do sum error is equal to sum error plus error. Now, technically, in order to calculate the integral of the error, every time we add on the error, we need to multiply this times the amount of time that has passed. Let's go ahead and do that. Times 0.1. That will help keep our sum error from adding up too fast. Now, do some tests. Change ki to a couple of different values and observe the effects of moving the marker or the red object around in the view of the camera. This process of trial and error, picking a gain and then observing what happens, is one way to tune your controller. But in the next lab, we're going to learn how to tune a controller from a model of the system. We'll actually create a model of the system without the controller and then use that model to design a controller. For now, try to make some observations by eye. What happens when you change the values of proportional, derivative, and integral control?